Hi all. So we are looking at course ECL201, which is Scientific Computing Lab. Okay. So in this lecture, we are going to look at the next experiment, which is basically numerical integration and differentiation. Okay. So before I show you the code, I will just walk you through what we are going to do, and then we'll look at the code. So the main objective of this tutorial is the first one, that you should be able to plot functions using a special package called as matplotlib, and using vectors. So this you might have already studied, or the previous tutorials might have already given you a glimpse of how you can do this, but we will also look at this one. Second part, we will see how we can use Python to do differentiation. Third part, we will see how we can use Python to do integration. And in third part, we will see how integration can be done, or the absolute value of integration, where we will try to make sure that integration is just like as we do in our paper, or we can do approximate integrations using trapezoid rule and Simpson's rule. So these are the things that we are going to look at in this experiment. Okay. So before going to all these programs, we will see each one, and we'll just see a summary of what all these things are. Okay. The first one, you are going to plot functions. For example, you know that you have the cos function, sine function, tan function in Python. So we are talking about all these functions in Python. Okay. Similarly, you have cos h function, which is the hyperbolic cos, sin h function, tan h function. And how did we generate the values of this? When you say cos of the value of angle, for example, if I say pi, or to be more specific, if I say cos of math.py, where math is the package, then you see that this value will be -1 in the program. So we have seen that if you want to create one single value, or if you give a single value inside this cos function, it will generate the corresponding cosine value. Similarly, you can do it for sine, tan, cos h, sin h, tan h, etc. Instead, let's say I want to generate 10 cosine values. So how will you do to generate 10 cosine values? So you can do, for example, you want to generate values for angles, let's say 0 degree, 36 degree, 72 degree, 108 degree, and go on till 360 degree. So there are like 11 values, but let's say there are 10 values. So you can do cos of 0, then cos of 36 degree, which should be converted to the radians, which is 36 degree multiplied by math.pi by 180. Sorry, yeah, 180. Okay, and then you can do cos of 72 degree multiplied by math.pi by 180 and so on. Okay, so what we have done here is that this is basically you are converting into radians. So this is convert 36 degree into radians, because the angle inside the cosine function should be radians. But the problem here is you need to give the values each time to generate the value. Like first you do cos, you put 0, then you do cos, then you say 36 degree multiplied by math.pi dot 180 by 180 and so on. Instead, you can define a vector. Okay, that means I can define a vector called as angle vector, which I takes, this is basically something called as a list, which takes the values 0, 36 degree, 72 degree, 180 degree, sorry, 108 degree up to 360 degree. Okay, where this dots actually means there are values. Now you can convert to the vector angles to radians by just multiplying the angle vector, which is that variable, if you multiply it with math.pi by 180. So now whatever angle vector variable have, it has the corresponding radian values. Now if you do, let's say cos val is equal to cos of angle vector radians, then the cos value will now have the values, the cosine of 0, which is 1, cosine of the angle 36 degree, which will be some value, let's say this is cos 36 degree, comma, up to the cosine of 360 degree, which is 1. Okay. Now if I plot, so this gives my cosine values. If I want to plot this, so basically what is the logic behind plotting? So this should be angled, and this should be the value of the angle of the cosine value, for example. Now I can write, okay, this is my 0 degree, 0 degree, let's say this is 36 degree, 72 degree, 108 degree up to 360 degree. Okay, so I plot here in the x-axis these angles, which is the angle vector. Okay, and in y-axis I will plot the variable cos val. Okay, so for 0 degree, so if I write angle vec also below this, so this is 0, 36 degree, 108 degree up to 360 degree. So so this is my x-axis, sorry, this is my x-axis and this is my y-axis. So if you look at here, for a value 0 in x-axis, the corresponding value is 1. For a value 36 degree in x-axis, the corresponding value in y is cos 36 degree. For a value 108 degree, the corresponding value is this, and for 360 degree, the corresponding value is this. So if I do plot, basically you should use matplotlib, but I am saying, let's say matplotlib.plot of angle vec, comma, cos val. It will plot for 0 degree, it will plot 1. For 36 degree, it will plot the corresponding cos val, which is this one. And so basically it will plot for each value. For 72 degree, it will have some lower value. There is some 90 degree coming here. So it will generate the plot and it will connect it through the dots. So it will get some plot like this. Sorry for my drawing. It will get something like this, or let me draw it correctly. Okay, so that is your cosine wave. Similarly, you can plot, if I give here instead of cos, if I give here, or if I give here sine, you will get the corresponding sine plot. So by using this notation called as the vector notation, so basically this is the vector. So by using this vector notation, you can easily create the corresponding cosine sine values. Now if you look at this vector notation, you see the spacing between any adjacent elements. For example, 0 and 36 degrees, 36 degree, 36 and 72 is 36 difference, 72 and 108 is 36. So the difference between any two adjacent element is same. So you can plot it, you can generate the value with functions, which is a single function which can generate it easily. Okay. So this is your first step where you do functions using vectors. Next is differentiation, which I am not going to elaborate too much, because anyway we will do two types of differentiation in Python. Okay. So for this you need to use SciPy. So there are multiple ways. One is you can use SciPy, or you can use NumPy, and we will see both ways how you can do this differentiation. So these are packages. So make sure you install these packages. Okay. So if I want to install this, if you are using a Windows system, it is pip install SciPy for SciPy, and if you are using NumPy, it is pip install NumPy. Okay. And I am not going to elaborate too much on differentiation because it is straightforward in the Python. I am not going to discuss too much. Next is integration. Okay. So what is integration basically? Let's say I have a function y of t is equal to, let's say it is t square. Okay. So y of t is equal to t square represents something like a parabola. Right? So it's something, it's not exactly correct, but I am saying that this is like a parabola. Now if I do integration of y of t, let's say this is 0, this is 1, 0 to 1 y of t is equal to 0 to 1 t square dt. So that's a dt here, sorry. So what does this integration means? This means area of the curve, or area I would say under the curve, between 0 and 1, okay, which is this. Okay. So, similarly, you can have any such kind of integration. For example, y of t is equal to t cube plus 2t square plus 1, right. So, in this case, let us say my y axis is this, sorry, okay. Let us say my curve is something like this, okay, and I want to integrate it along, let us say 0 to 3, okay. So, let us say this is 0, 1, 2, 3. So, if I do it here, basically you find the area under this curve. So, the normal way is you consider a small strip okay. Find the area under this strip and you move the strip till you reach the last point. So, this is how the definition of area is. This you might have studied in all your +2 classes, etc. Okay. This is the regular integration, fine. And in MATLAB you can do regular integration in multiple ways. We will see, sorry, in Python you can do regular integration in multiple ways, and we will see 2 different ways of doing this integration. But what I want to discuss here is you want to do something called as integration by trapezoidal rule. Okay. This is actually an approximate integration or approximation. Okay. So, if you are not concerned about the performance of your code, then you can do the normal integration. Like if your system is high-end system and it can do very well any type of computation, then you can do normal integration. But let's say your system is very bad and it will take a longer time to do integration, then you can go with trapezoidal integration, in which your result will have some amount of error. Okay. So, what is trapezoidal rule? So, if you have some kind of a function which is something like this, okay. In trapezoidal rule, what you will do is you generate all these points of the function. Let us say you generate, because this function is of the form y of t is equal to some value, let us say t square plus 2t plus 1. So, if you substitute for t equal to let us say 0, 1, 2, 3, etc., you will get the corresponding value of y of t. Okay. So, let us say this axis is t, this is y of t. So, these points are the corresponding values of y of t. Now, what you will do is you can draw a straight line from each point. So, these all things you do not want to do in the code. I am explaining what a trapezoidal rule is. Okay. And you can join these points. You can join with a different color. Okay. Basically, if you look at it closely, it is not exactly a rectangle. It is actually a trapezium. That means I can put it as one rectangle, which is the black, and one triangle, which is the top blue. So this is also every such trapezium you can find it like that, right? Now if I find the area of this rectangle, and you know what is the area of the rectangle, you know the height and you know the width, you find the area. And if I find the area of this triangle, again you know the length, you know the height, then basically you will get the area of this trapezium. And if you add the area of each of this trapezium, then you will get the total area under the curve. This is called as the trapezoidal approximation or trapezoidal rule. So in Python you have a built-in function which will give you this value. Okay. Next, so basically you want to create the points y of t, which we have given as dots, red dots, using points t. So the more number of points you generate, the better the value of the integral will be. Okay, that is trapezoidal rule. Simpson's rule is similar to trapezoidal rule, except that the approximation in trapezoidal rule is a linear approximation. In Simpson's rule, it is a quadratic approximation. There is a formula for this. Okay, and this has less error when compared to the trapezoidal rule. The error is if you compare the integration output of Simpson's rule or trapezoidal rule with the original integrated value, what is the difference? That is the error. Okay, so again I am not discussing what is the formula and all. There is a bit of a formula in that one. So here what I am doing is, you have the same curve, okay, and you are saying that, okay, instead of approximating, you generate all these points again, okay. Now you can draw the lines. Okay. Now instead of approximating it with a straight line, so here we have connected here a straight line. All these connections are straight line. Instead of connecting it with a straight line, we do it with some kind of a curved or a quadratic approximation, something like this. Okay. So if you compare both this, you see that this one is following that function more closely than that is for trapezoidal rule. Okay, so this gives very much less error. But in both the cases, you need to generate the points of t, which is this, all these points, and you want to find the corresponding points of y of t, which is basically you want to put it inside the function and generate these points. Okay, so this sums up what we are going to do in the Python code. This is basically a theoretical background, so that you will find it easier to understand. Okay, so we will go to the Python code now. Okay, so these are our questions for experiment number 4. So basically, we need to realize the functions sin t, cos t, sin s t, cos s t, etc. This we have already seen during the lecture, that how we can realize using the vectors. And then we want to find the first and second derivatives of this function. We want to plot the derivatives functions and appreciate. We want to look at the numerical integration tools, and then we want to realize the functions like for example f of t is equal to 4t square plus 3. Then you compute the integration of that f of t from minus 2 to 2, or we can do any such integration. You want to repeat the above step using trapezoidal and Simpson's method, which we have already seen what a trapezoidal and Simpson method is, and then compute the integral of one such function. So let's look at the code for the first one, in which we say you want to realize the function sin t, cos t, sin ht and cos ht, or similar trigonometric function. So basically we use the numpy package, and I import the numpy package as np. I also import math because I will be using pi in this one, because there is cos, sin, pi, etc. And you need to use matplotlib, which is for plotting purposes, and I import this as plt. Next, I want to first generate a vector. So to generate a vector, I should have a starting vector, ending vector, and the difference between any two vectors. Okay, that's we have seen in our lecture. So I say our x-axis is basically the angle. So I am going to generate the angle in degrees. So my starting angle is 0, my ending angle is 360, and the difference between any two angles is 10. To generate such an angle, instead of directly typing 0, 36, 72, etc., what I do is I will first find out the number of angles between 0 and 360 separated by an angle of 10. So that is end angle minus start angle divided by the difference between any two angles will give me the number of angles. I will add plus 1, I will say why it is. So if I print this, basically I will get the number of angles. Okay. Now to generate all these angles, you have a function called as linspace, which is from numpy. So np.linspace will generate values starting from this, which is for example 0 in this case, ending with this, which is for example 360. In between, the number of values between these two values is specified here. So from 0 to 360, you should generate 10 such angles, or this much number of angles. Now why I did plus 1 here is I want to generate from 0, 36 degree, 72 degree and so on. So the total number of angles is actually 11, including 0. Also, so add a plus 1 here, so that I will say you generate 11 angles between 0 and 360, so that I will get 0, 36, 72, 108 and so on. So this is in degrees because I specify it as 0 and 360. I need to convert into radians. So whatever, so this is basically a list. Okay, so I'm just going to print this. I'd say angle in degree list. Okay, and I say angle in degree. Okay, I am removing this because I don't need this much. Okay, fine. And if I print the angle in radians, you will see the value of angle in radians. So this is angle in radians list. This is angle in radians. When I put the sign of this, okay, that means np.sign will give me the sign value of whatever is inside this argument. So here I am giving the list, angle in radian list. So it will give you all the values of sine in the list or the angles in the list. So if I print sine value, sine val, I'll get the value. And then I'm going to plot. Okay, so let me just hold this plot for a moment so that you will understand how we can. Okay, so I am going to run this code. So let's see this. Angle in degree. So I hope you can see this. Angle in degree is 0, 10, 20, 30, 40, 50, 60, up to 360. Okay, and the difference between the angles is 10, and you have actually the number of angles is 37. Now, angle in radians, you see some 0.174, etc., etc., which is basically 10 into pi by 180. 20 into pi by 180 is 0.349. 30 into pi by 180 is 0.5235, etc., etc. The sine value, if you see, the first one is sine of 0, which is 0. Second one is sine of 0.1745, which is 1.736. And third value sine of 0.349, which is 0.42 into e raised to minus 1, which is 10 raised to minus 1, and so on. So you have generated all the angles. Okay, now let's plot it. Okay, so for plot, we have seen in the last lecture that you should use the matplotlib, in which you have the package, in which you have the class pyplot, and you import it as plt plot. So you plot it as figure 1. The x-axis should be in degree, the y-axis should be the corresponding sine value, and I am enabling the grid so it will look nice, and I am just plotting. Okay, so let me just run this code. Sorry, I didn't save the file. I'm sorry for that. So the plotting will take some time. So you see, you have plotted a sine wave. Let me increase in size. You see at 0 degree, you have a value 0. At about, let's say, 90 degree will come something around here, which will be the maximum, which is 1. At about 180 degree, which will come something around here, which will be 0. And it goes on. So you see, you have plotted one single frequency of sine wave. If you want to plot two such waves, you can just give angles from 0 to 720 degree, so that you will plot two such sine waves. But if you want to plot any particular frequency, then you want to go for some logical program. Okay, so that is regarding the sine plot. Fine. Now let's look at the second part of our question, which is basically to compute the derivatives, the first and second derivatives. So here we are not using grad, we will be using Python, but with Python you have different packages which can be used. Okay, so basically I have two packages, one is numpy, and then I will use scipy and simpy. Okay, so I will use scipy and simpy for derivative, and we will see two different methods of finding the derivative. Okay, so we will come to this function later. Again, we are having a start angle, we are having an end angle, we have a difference of angle, and we found out the number of angles. We can print the angles. Currently I am not printing the angle, and you can angle in degrees, angle in radians, etc. That is okay. Now, to find the derivative of, let's say, sin x, what you can do is, there are two methods. Either you can define a function of the derivative of the function that you want to find. For example, since I want to find the derivative of sin x, I will define a function which accepts an argument x and returns the value of that argument using the function. So I want to find the derivative of sin x, so I will return np dot the sine of x, and then you call the derivative of the function. So you see the func val is actually this function. So you call that func val. Once you call the func val, you want to find out after the differentiation what will be the value if you put the angle. So you give the angle in radians. So the first argument is the function for which you want to find the derivative. The second argument is, after finding the derivative, what should be the value at each angles. Okay, so the angles that you specify here. So I have given a complete description of how to look at the derivative function. So there are multiple parameters. First parameter is function, second parameter is x0, the point at which the nth derivative is found. Okay, so this by default will find the first derivative. If you want to find second derivative, there is an option called as n. So you just say comma n equal to 2 will give you the second derivative. So by default it will give you the first derivative. Okay, so let me just comment this and let's see what is the output of this code. Or maybe I haven't printed this, so let me print this also. Let me print the original function. Which is basically func val of angle in radians, and the derivative is basically dy dx. Okay, so let me try to run this. Let's see if I get the correct results. Okay, so there is, I think, an error here. The y should be kept. Sorry. So let me just clear the screen. So you see the value of the function is the sine value. So this is actually the sine value, 0, etc., etc. When you found the derivative of the function, you see it's actually the cosine value. Okay, this is actually 0.8, which is very near to the cos 0. There is a approximation error in Python, because of which you are getting a different value. I hope this is correct. Yeah, I think it's correct, because there is a minus value because of there is a minus sign. Fine. Okay, so it have found the derivative. Now instead of using this func val, there is another way. You can use something called as a lambda. So when you say lambda x, you say x is something called a symbolic variable, that you are not going to put the value of x now, it will be put some other time. So in that case, you can just say lambda x sin x. Basically you are defining a single line function, and if you can just say f. Okay, so f here, and you don't want to use func val, this should turn me the same results. Let me see if it was run. Okay, so there should be NP. See, so you see that it is returning the exact same output as that of the previous, which is initial value is 0, here the derivative is 0.8 and goes on like this. So if you are going to define a single line function which is like this, you don't want to define a function, instead you can specify it as lambda x. So x is the parameter which will be passed from another function. Okay, so this is the alternate way, right? And you can plot using this figure, you can plot both the derivative and the function. This is regarding using the derivative function which is actually from SciPy. Instead, let's say you want to see what is the result of the derivative. For example, result of sin x is cos x. I don't want to get the value, instead I want to get the exact result. Okay, so let me comment out this and let me uncomment this. Okay. So to find the exact value, you define using the SymPy package or symbolic package, where you define the symbol x as some kind of a symbolic representation. It says that x currently will not take any value. The Python should consider x as an alphabet. That's all. Okay. And since you are using SymPy package, there is a sign term, sign, which is defined inside SymPy. So I should import that sign. Similarly, any other trigonometric function. So I has imported as sim sign just to make sure that it is different from numpy sign. So I say sign, sim sign of x. Then I call the function derivative. So be careful, the d is capital in SymPy. And I pass the function, which is a symbolic function, and x. And then I say dy dx dot do it. So this is another function. So if I print this, the derivative is this one, and the original function is func. Okay, so this func, and let's say, or let me just run this and show it to you what this actually gives. So if I run this, you see the original function is given as sin of x and the derivative is cos of x. You see that it hasn't substituted any values, it just have shown that derivative is this much. This is exactly like your normal derivative where you are doing in pen and paper, and it will not assign any values. Let's say you want to evaluate this function for some value of x. So what you want to do is you want to do this. So you say after the do it function you will be getting some result, and you say this dot subs means substitute. Wherever there is x, you substitute its value m pi by 2, that is pi by 2 value. Okay, so you can write the value of the derivative at pi by 2 is this. Okay, so if I run this, you see the value of at pi by 2 is a very small value, 10 raised to minus 17. As I told earlier, Python have some approximation error. This is actually a very small value, which is approximately equal to 0. So cos pi by 2 is 0. So this way also you can do the differentiation. And if you want to do the second order derivation, or this is basically if you want to do the second order derivation or second order differentiation. Then you do this. Okay, so I can print the second derivative is this much. You can substitute the value and you can get the result. So let me clear this. Let me run it again. So you see, original function is sin x, derivative is cos x. The value of derivative pi by 2 is this one, and second derivative is differential of cos x, which is minus sin x. Okay. So this way we can do the differentiation. Okay. So this, all these files I will be sharing with you. Next is integration. So for integration, again we will be using SciPy and SymPy. Okay. So we will look at this function later. So for integration, you need to specify the limits. Integral minus 10 to 10, that is the minimum, which is minus 10, maximum, which is 10. And you want to specify the function. Again, the function specified here is x cube plus 3x square. That is the function which is specified here. So you define that function and you return in terms of the parameter or the argument. So the function or the function which calculates integration is called as quad. Okay. So you should import it from scipy.integrate. So quad of function value, which is x cube plus 3x square, specify the lower limit and upper limit. This will return the result with the error. Okay, error means if it cannot give you the exact result, it will give you the how much error is there from the exact result. Okay. So if I run this, let me comment out this. Let me clear this and let me do, I think it is Q6. So result of integration using SciPy package is 2000. So that is the result. Okay. I can also print the original value. So basically in result you have substituted the values x min and x max. Fine. Now there is the other way, or also last time when we have seen, we see that you can use lambda, exactly same. Here instead of function var you can use func, and it will do the exact integration, because you are using lambda x because there is a single line function. So you don't want to define all these things. Okay, it will also give you the same result. Okay, so if you integrate it and substitute x min and x max, you will get these values. There is another alternate way in which you can use SymPy package. Again, you define x as symbol. Remember, this S of symbol is capital. You define the function in terms of x and you integrate it. Okay, so let me just run this. Fine. So if I run this, you see the result of integration using numpy is x square. Okay, this is the integration. Okay. If I do, let's say, x or let's say 1 by x or x cube, 1 by x cube, just for showing you. So it says the result of integration using SymPy package is minus 1 by 2x square. Now in the next step, I substituted the value of x. Okay. So if I want to find the value of x between minimum and maximum, you can substitute x the minimum value, you can substitute x the maximum value and subtract both. So here I have just substituted the value of x as 10. So when I substitute the value of x as 10, I got minus 1 by 200. Okay, fine. So that's regarding this normal integration. Next one is using trapezoidal and Simpson's rules. So this we have seen how it is working. So we will use the same formulas. So we have already seen what this function is. We have x min is equal to 10, x max equal to 10. We have seen that we need to specify the points of the function. So you generate, let's say, 20 points between x min and x max, okay, and you evaluate the function of all these points. Basically, this is your y of t and this is your x of t. So you substitute in x of t all the values of this point. So if I print x or x of t is equal to, that is basically this index points, okay, and if you print y of t, that is equal to basically the value at x of t, okay. Then if you do traps, this is a function from SciPy integrate. If you do traps, then it will find out all the trapeziums connecting these points and find out the integrated value, okay. So basically, when you have, if you remember, we have drawn the line, we have drawn the trapezium which consists of a rectangle and a triangle. We have added all the areas of them and we found out that that will be an approximate integration. The traps function will do the exactly same, okay. So it will not be exactly same as that of original integration, it will have some errors. So let me just comment out this to show you the actual value. So if I run this, okay, you see x of t is basically the points that I have generated from minus 10 to plus 10, okay. So that is minus 10, minus 9, minus 8 up to plus 10. And y of t is, if you substitute these points inside x cube plus 3x square, what is the value, okay. So x cube is 1000 plus 3x square is 300, 1000 plus 300, sorry, minus 1000 plus 300 is minus 700, and you have given all these values. Now when you did the trapezoidal integration, we saw that result of integration using trapezoidal rule is 2010, and this is your actual integration which is using the quad function, and we see that the actual integration value is 2000. So there is an error of 10 because we have used only around 20 points. If you use around 100 points for x of t, you see that this error reduces. So I haven't tried this, but let me try that. So if I put n equal to 100 and if I do the same integration again, you see that, okay, there is too much of error, okay. So there might be some mistake that I have made, but this is the general idea, okay, fine. Now similar to trapezoidal rule, I can use the Simpson's rule. So just uncomment this. Exactly same, you specify x min, x max, number of points, you specify the number of integral points, or the value of integral points which is same. So I just copy paste this, and y of t is also a similar thing. And instead of using traps, I'll use sims, and we have seen sims is also an approximation of integration, and we will see that sims has much better result when compared to traps. So let's run the whole thing. So you see that using trapezoidal rule it is 2010, but using Simpson's rule it is 2000. So the result of integration using SciPy package or the normal integration is almost equivalent to that in Simpson's rule. So both the integration matches. So Simpson's rule will give you more accurate result because it is a quadratic approximation, while trapezoidal rule will give you a less accurate result because it is a linear approximation. Okay. So this is regarding the integration. So we'll post some assignments, and based on this I'll also post all these codes and the recorded video. You can try to do it by yourself. Okay. Thank you.